So far, we've established that to calculate the angular momentum of a rigid body about some point, we'll have to calculate a certain integral. Is it always the case that we have to calculate an integral for a randomly shaped body to find its angular momentum? Well, actually, we don't. We'll introduce inertia terms, moments of inertia, that we can find in tables that will enable us to calculate the angular momentum without actually going through and calculating these integrals. For this, we will use the velocity analysis equations. Recall that for any material point on a body, we can relate the velocity of that material point to the velocity of the center of mass by omega cross r minus rc. And let's define this r minus rc vector and call it pi, small pi. So that's the position vector from the center of mass to a differential mass dm. That's called pi. And we're gonna equate components x ex plus y ey plus z ez. So ex, ey, ez, that's a rotational basis. So as the body moves, the x, y, and z are gonna remain constants. The rotational bases are gonna move in time. So if I go back to my expression for hc, that was equal to the integral of r minus rc of v dm plus v dm over the body. So the integral over the body of r minus rc, I will replace v by its value from this equation, which is equal to omega cross r minus rc plus vc dm. So that's the integral over b of pi. It's lowercase pi, so let me fix that. Lowercase pi written like that, crossed with vc plus omega cross pi. dm. I will split this integral into two. That's the integral over b of pi cross vc dm plus the integral of pi cross omega cross pi dm. Then in this first integral, I can take vc outside and I can calculate the integral of pi dm crossed with vc, and that's simply equal to 0. Why? Because that's the integral. Pi is, remember, r minus rc dm, which is the integral of r dm minus the integral of rc dm. That's by definition the total mass times rc, and for this I can take rc outside. The integral of dm, that's the total mass times rc. Now the second term is the integral of pi cross omega cross pi dm. To simplify this term, we're gonna use the back cab identity. So let me open up Google very quickly and check what this identity is. We're gonna use that. I'll guess it first and then we'll double check on YouTube or on Google. A cross B cross C is equal to B cross A dot C, or I think it's A dot C, I don't B. Let's fix that. B. A dot C minus C A dot B. Let me double check if I got this right. Okay. I should have opened Wikipedia. Okay, this says the A cross B cross C is A dot C and A dot B, which is what I have. Okay, that's great. So I'm gonna use this identity to simplify that term. Okay, so pi cross omega cross pi is equal to B, which is omega dot pi, or omega along pi dot pi, minus pi and pi dot omega. So now HC becomes is the integral over the body of omega pi dot pi minus pi along pi dot omega dm. Now if I replace, remember, pi by r minus rc, which is equal to xex plus yey plus zez, and omega by omega xex plus omega yey plus omega zez, I'll get the following. I'll get that hc is equal to icxx omega x plus icxy omega y plus icxc omega z along ex plus icxy omega x plus icyy omega y plus icyz omega z along ey plus ixc c omega x plus icyz omega y plus iczz omega z ez, where the I terms are called moments of inertia. Actually, the ixx, iyy, izz, these are called the moments of inertia. Moments of inertia. About z, about c, and the ixy, ixz, iyz, they are called the products of inertia. And these are symmetric, so that's equal to icyx, that's equal to iczx, and that's equal to iczzy. And their expressions are as follows. icxx is equal to the integral over the body of y squared plus z squared dm. And icxy is equal to minus the integral over bxy dm. This minus sign is conventional in O'Reilly's book. In Miriam and Craig, they do not put a minus sign here, but they'll they just do not put a minus sign here. They will put it here. Instead of a plus, they'll put a minus over there, I think. And from here, you can deduce the expressions of the other moments of inertia. So, for example, iccc is just the integral over b of x squared plus y squared. Yeah. Okay. then this expression we can easily write, or more easily write, in matrix form. I can say that hc dot ex, hc dot ey, hc dot ez is equal to ixx, ixy, ixc, iyy, izz, and iyzc, and this is symmetric. W dot ex, W dot ey, W dot ez. And of course, when in this class, if omega is just omega z ez, so omega x is equal to 0 and omega y is equal to 0, then hc is gonna simplify. It's gonna be equal to I cxc omega z ex plus I c yz omega z ey plus I c z omega z easy. Okay, that's it for this video. We'll do some applications in the next one.